In this video, we're going to compare the E1 and E2 reactions, specifically looking at their stereochemistry. And when thinking about their stereochemistry, we're really going to look at their stereochemistry in cyclohexane rings. So here I've drawn out two examples of elimination reactions, and the first one should be recognizable as an E1 reaction. Let's have a look at it in a little bit more detail here. So we've got a tertiary carbon. We've got water present in the presence of heat. So water is a very weak base, right? Weak base. And our product here is an alkene. And we also, in these conditions, get a fair amount of SN1 product, which I haven't drawn out. But the alkene is our E1 product, which we'd obtain as sort of a minor product in this reaction. One thing to note about this product, and look at how many carbons are attached to the alkene here. We've got 1, 2, 3, 4. So this is a tetra substituted alkene. This makes sense when you think about it, right? Remember Zaitsev's rule. Zaitsev's rule tells us we always want to form the most substituted alkene. That's Zaitsev's rule. Now let's look below at the second example of an elimination reaction. So let's say we've got this same substrate, so tertiary alkyl bromide here, and we're treating it with OH minus, actually a little bit more correct. Let's put the counter ion in there, sodium. So let's say sodium hydroxide in the presence of water. We're heating, and we get this alkene. This is our only product. We only get this product. We don't get anything else. And one thing to note about this alkene is that it is not the same product, first of all, right? We're not forming an alkene between these carbons. We're forming what we call a tri-substituted alkene. Now, this is really weird. So why is it that in this top example, like I said, we went through an E1 type process, we get a tetrasubstituted alkene. And in this bottom example, we're using a strong base. And this goes through an E2 reaction. We're getting a tri-substituted alkene. So it looks like we're breaking Zaitsev's rule here. What is going on that we're getting this tri-substituted alkene in the bottom example, but a tetrasubstituted alkene in the top example? So what's going on? Has to do with the stereochemistry of the E1 and the E2 reactions. So we're going to look through these in a little bit more detail so that you can understand why is it that we'd get different products under different conditions, and also what is it about the stereochemistry of each of these reactions that leads to different products. Okay, so let's look at the E1 reaction first. Remember what happens in the first step of the E1 reaction? The leaving group leaves. The leaving group leaves, and this is going to lead to the formation of a carbocation. Let's draw that out here. So carbocation, CH3 stays the same, and this CH3, and let's maybe put numbers on things here, 1, 2, 2, 3, 4, 5, 6, and this would be 1, and we should draw the carbocation is here. We're going to have the bromide ion floating off into space here, 3, 4, 5, and 6. That's going to be our first step, which is the carbocation. Now, to understand what happens, what gets us to the alkene from here, it's still worthwhile to look at the stereochemistry of the cyclohexane. And remember that cyclohexanes are not really flat like we've drawn them here. We actually have a cyclohexane chair form, which we need to look at. And the one way to convert this into a chair, and let's just, that triple thing here looks for the equal sign. That's sort of our way of saying this is the same as this. Let's just sort of arbitrarily number our cyclohexane. And since the only thing is, since we're going clockwise in our numbering here, we should go clockwise in our numbering here. And let's just call this carbon number 1, 2, 3, 4, 5, 6, and draw in the headrest axial, the footrest axial, and then all the other axials alternate like so. And then we can draw in our, we're going to have to rub out one of these in a second, but we can draw in our equatorial groups. Okay, and there's our cyclohexane. And since we said carbon 1 was a carbocation, let's just erase that. And let's put CH3 here in positive charge. And carbon 2, let's look at what carbon 2 would look like. Well, what's up? So up, or wedge, would be CH3, that's as we're looking down. And the up group here would also have to be this CH3. So this is a wedge, so it's pointing up. And as we look down on the cyclohexane, okay, the first, if my eye is here, the first group I'm going to run in my eye into is going to be the CH3. And the hydrogen would be over here. Okay, so what about an elimination reaction coming from this conformation? Think about what would have to happen here. So remember, we can look at these through the lens of a Newman projection. So if we were to look along carbon 1 and carbon 2, we would see something like this. We'd sort of see CH3 pointing off to about 9 o'clock here. We'd have the R group, which would be carbon 6, pointing off to the right. And we'd have our p orbital like this. Carbon 2 would be in the background. We'd have a CH2 here, and then we'd have this orange H would be pointing off sort of down to the left, like over here. And then we'd have the other R group, so this would be carbon 3 over here. And notice that there's not actually very good overlap here. There's actually this p orbital, empty p orbital with the orange hydrogen. There's actually poor overlap. So no elimination reaction can really occur well here. This is not a very good setup for an elimination reaction, in that there's not good overlap between the pair of electrons which are going to form the double bond and the empty p orbital. But that's actually okay. That doesn't bother us, because what we can do is we can actually do the chaired flipped form of this species. We can draw it out like this. And we can make sure that when you're doing a chair flip, that you're not just flipping everything just on its back, that you really are taking your equatorial groups and making them axial, which is what I'm going to do here. Down, up, and we can draw in the CH3 later, the carbocation later. Make sure you draw your equatorial groups in as well. Notice how our green axial become equatorial and our orange equatorial become axial. And we can number this. Let's number this as the one thing we have to make sure of is that carbon 2 was axial green. Now carbon 2 needs to be equatorial green. So they can make it either here, or here. So let's do it here. Okay, so let's make this carbon 2, which would make this carbon 1, because we're going clockwise, 4, 5, 6. And let's just adjust things a little bit. So have CH3, and their hydrogen will be pointing down. That's still up. See, it's still up. When we flip the chair, we don't move up to down. We move axial to equatorial, and vice versa. Now carbon 1 is still a carbocation, so it's going to be floating off here, positive charge. And now if we look at the Newman projection along C2 to C1, let's say, we would look like this. So we'd have the hydrogen would be at 6 o'clock. This would be our orange hydrogen. And we'd have our CH3 pointing off to about 2 o'clock. We'd have our R group, which is C3 over here. We'd have our CH3 from the carbocation here. We'd have our R group from carbon 6 here. And the best part is that we'd have overlap of this empty p orbital with the CH. So now we've got great overlap. And the E1 can happen. So this means that our base, well, let's say that it's water, is going to take a proton away from here, and we can show this occurring, and this would give us our alkene. So the bottom line here is that we can always do a chair flip to give us the Zaitsev. We said this is the Zaitsev, right, because we're going to form the most substituted alkene. We want to form the double bond between carbon 1 and carbon 2. We can always do a chair flip to give us the Zaitsev with, when a carbocation is present. Carbocation is present. So this is always the case for the E1. So E1, we can essentially always form the Zaitsev product. We can always do a chair flip to make sure that our p orbital is going to overlap with the hydrogen that we're removing. Now, let's look at the E2. The situation is going to be a little bit different. So here we've got our E2, and same substrate, no different than the one we did before, but we're going to get a different product out of this. And the point of this part of the video is to show you why. So let's just do what we did before. So let's just number our carbons, as we did, and let's redraw the we can draw in what's going to happen in the E2. Remember the E2 is a little bit special because the stereochemistry is important. So stereochemistry is important, so that means that the hydrogen and the leaving group, so Lg, they have to be what we call anti-periplanar. So essentially 180 degrees from each other. Okay, so let's have a look at what this might look like in its chair form. So let's just draw this out like that. Okay, and we can number, it doesn't really matter where we number things. As long as they're clockwise, that's good. And this is our headrest, so we can make it axial, and we can alternate. Just want to make sure. Okay, that's good. Alternate up, down. Okay. Then put in the equatorial. So this is up, make this somewhat down. This is down, make it somewhat up. Angle it away. So now we all have tetrahedral carbons here. And we said this is carbon 1. And here is our CH3. And here is our Br, right? So CH3 is a wedge. So as we look down on it, it's going to be pointing up. So the first thing my eye sees when I look down is the CH3 is pointing up at me, right? It's a wedge, it's pointing up at me. This Br is pointing back down. So CH3 is going to be axial here. And then that means that carbon 2, this is up, but up in the sense that this is equatorial here. This is equatorial. And if you look, notice that in the way we've drawn this here, our bromine is equatorial. And if you've seen previous videos in this series, you'll know that we can never do an E2 when the leaving group is equatorial. And the reason is because actually you'll notice that if you look at what's anti-periplanar to this bromine, you'll see that it's anti-periplanar to this red carbon to bromine bond is actually anti-periplanar to this red carbon to carbon bond. And therefore, we can't eliminate a carbon-carbon bond. We can only eliminate a carbon-hydrogen bond. So that is not going to be able to happen. But what we can do is we can do a chair flip. And we can see what we get from a chair flip and see what type of product we'd get from that. So let's draw out product of our chair flip here. So let's, again, what we should do is just make sure when we do our chair flip, well, let's make sure that all of our axial become equatorial and all of our equatorial become axial. So that means that all of our orange, which are equatorial here, now have to be axial. And so we'll draw those in like that. So always headrest, footrest, then alternate everything else. And then you want to angle your equatorial away from your axial like that. And so carbon 1 is green and axial. So if we want to number carbon 1, we want to make sure that it's green and equatorial. So it could be either this, or this. And let's make it this one. It's the closest one. Let's make this carbon 1. And we have to number it in the same direction too, don't forget. So we're going to carbon 1, 2, 3. I arbitrarily made this clockwise, but once you make the decision to number clockwise, you got to be consistent. Otherwise, you're going to end up drawing, it's going to get complicated. You're going to draw the enantiomer. So carbon 1, what would it look like? So the green bond was our CH3 here, and the orange bond was our Br. So now we've got an axial Br. And carbon 2, what do we have here? Carbon 2, our orange bond is a CH3. So we can draw in the rest of the hydrogens if we want to. Sure, why not? H, H, H. Okay, so then let's have a look at the eliminations we can have. Notice now that our Br is now axial. Our Br is axial. So let's look at trying to form our Zaitsev product along the carbon 1 to carbon 2 bond. What would this Newman projection look like? Newman projection can help us trying to figure out what this product is going to look like. So Newman for C1 to C2, if this was my I and I'm looking along C1 to C2, well, I'd look, remember it's kind of like a clock, right? So my bromine would be at 6 o'clock here. My CH3 would be at about 10 o'clock. And then I'd have my carbon 6, so my CH2, which is C6, would be pointing at about 2. And then in the background, I've got my CH3, and you see this is going to be a problem. And then I've got my green H, and then I've got my black CH2. We'll call this carbon 3. Now, what do we notice when we look at this? Notice that our bromine is anti-periplanar to CH3. So we can have no elimination between here. No elimination possible. Why not? Well, we'd have to break a carbon-carbon bond. And remember, in the elimination, we always break carbon-hydrogen bond. We have to have an angle between the hydrogen and the leaving group are anti-periplanar. So we cannot form the Zaitsev. Why not? Well, because we don't have the right stereochemistry. So we can't possibly form the Zaitsev, unfortunately. So we'd have to look for another situation where we might be able to see a carbon with which is anti-periplanar to a hydrogen. And actually we can find that if I change the position of my I. So if I instead of looking along the C1 to C2 bond, let's say I looked along the carbon 1 to carbon 6 bond. Let's make it a little bit better here. Ah, there's the I, it's returned. There we go. Bye. Okay. Let's say I looked along carbon 1 to carbon 6 instead. What would that Newman look like? Let's erase some stuff and get rid of our Newman. Okay. We draw a different Newman. We're going to see that this is actually going to work. So if we draw the Newman for C1 to C6, we would get this. So here's our thing, and then our bromine is pointing straight down, right? 6 o'clock. Our CH3 would be pointing to the left, like at 10 o'clock. And then we'd have our C6, CH2R, which would be C6, pointing there. And then what's going to be pointing straight up? This hydrogen is going to be pointing at 12 o'clock. And then this hydrogen is going to be pointing a little bit to the right and down. So at 4 o'clock. And then we'd have, let's see. Did I make a mistake? I did. I'm so sorry. I should have flipped the position of the CH2 and on the ring. Okay, so let's do that. Redo that. So the CH3 would be over here, and yeah. So then this CH2 would be here. We draw R, and so that would be. So the one that we're seeing in the front is carbon 2, the one in the back is carbon 6. Now the key point here is notice that we've got the hydrogen and the bromine. These are now anti-periplanar. So this actually works. So we can form a double bond between carbon 1 and carbon 6. This E2 reaction will work. So I know things are kind of crowded in here, but you imagine, let's draw it in a little bit more bold. So if I had my hydrogen, my base, let's say OH minus, can come in and take this hydrogen away. And notice that we've got this perfect anti-periplanar alignment between the hydrogen and the bromine. And we're going to break the carbon-bromine bond, and that's what's going to lead to the formation of our alkene here, where carbon 2 is still an alkene, still part of it still has that axial methyl group, and we formed a double bond between carbon 1 and carbon 2, carbon 6, 5, 4, 3. Okay, so just to review, that is how stereochemistry can impact the E2 as opposed to the E1. So in the bottom line here is that we cannot do a chair flip. We cannot form the Zaitsev no matter what through a chair flip. So in other words, in this case, we have to form the trisubstituted alkene because forming the tetrasubstituted alkene product is just not possible here.